Hi everyone. The goal of this video is to review systems in three variables, and by the end of the video you should be able to identify the three types of solutions to a system of equations, and these types of solutions will apply to both two and three variable systems. So I'm going to look at two variable systems to begin with because this is what we should be familiar with. There are three different types of solutions for a two variable system. You can have two lines that intersect at one point, so you'd have exactly one solution. So that could be like 2, 3, okay, where x is 2 and y is 3. That's how you'd write your solution. Okay, or I can have a solution where the lines are exactly the same. So you see the blue line and the green line overlap. That means any point on the line is a solution. So there will be infinite amount of solutions. Or you can have two lines that are parallel with no intersection, which would mean that there was no solution because there's nowhere that they have points in common. So these are the three different types of solutions you should have learned about in previous math classes. The new stuff on here is some vocab that you may or may not have seen before. So the first word you see is the word consistent versus the word inconsistent. Now I'm going to say what this means without writing it down, but that doesn't mean you shouldn't write it down. So write your own definition. What consistent means is that there is at least one solution. So if they intersect at a point, that's consistent because it has a solution. Or if they overlap, there's infinitely many solutions, it's consistent because there's still a solution. Inconsistent means there's no solution. So these two are consistent. This last example is inconsistent. And you can break down consistent further, and you can break it down by calling it consistent independent or consistent dependent. Now the way I think of the difference is these two lines are dependent on one another because they're the exact same line. So all of the solutions are the same, they're dependent on one another. Whereas this one, while they have one common point, the rest of the solutions or points on the lines are independent of one another. Okay, so that's the difference between this vocabulary. You should know to label your solutions consistent versus inconsistent and independent versus dependent. Okay, here's another graphic to kind of show you two variable system, and it shows you how you get this out of an algebraic equation. So if you get one solution, that's like where you solved and you got x equals 2 and y equals 4. But if you got an infinite solution, that would be an equation such as like, I got a true statement, like something like 6 equals 6, or 0 equals 0, or negative 1/2 equals negative 1/2. So if you get a true statement, that means no matter what you do to solve those equations, no matter what you plug in, you're always going to get a true statement. So that's why there's an infinite number of things that work, because you can plug in infinite things and still get a true statement. Whereas if you get a contradiction and everything cancels out and you get like 0 equals 4 or negative 12 equals 12 or whatever is false, that means nothing that you plug into the equation will give you an equality. So there's no solution. There's no points where they intersect. Now in this class, we're going to talk about systems in three variables, which means we're really in three dimensions, which means we're talking about planes that intersect versus lines that intersect. Okay, so there are three different ways you can have planes intersect, and it's the same as the way lines intersect. So you can have the three planes and think about like three pieces of paper. You can merge all those three pieces of paper so they have a common line. That's what this shows you. They all have this line where there would be an infinite amount of solutions where they intersect, because they intersect here, but they also intersect here, here, so on and so forth. You can go infinitely on that line. Or the three planes can have one point in common, which is what you see here. So that's the only place these touch, and that's kind of hard to visualize in this picture here. Or you can have three parallel planes. So if the planes are parallel, there's still no solution. Now let's do an example to figure out what kind of solution we have. So this is a little bit of a review from yesterday, but we're going to go through the steps to solve the solution to this three variable system. So three variables, three equations. First step is to create one two-variable equation using either linear combination or substitution method. Linear combination basically just means elimination. I call it linear combination because it's got some linear algebra applications that we'll be reviewing through this chapter and you'll see in future math classes. So I'm going to label these 1, 2, and 3 just so you know what I'm talking about. So I'm going to pick two of those to combine so I can create a two-variable equation. So right off the bat, I don't know, you can eliminate whatever you want. I see the z's are kind of all similar, so I'm going to choose to eliminate z's in my first two steps. So first, maybe I'll combine equation 1 and equation 3, because I have a plus 2z and a minus 2z. So I have 3x plus 5y minus 2z equals 13. and I'm going to linearly combine or eliminate with 14x, negative, minus 17y plus 2z equals negative 19. Okay, so if I add those together, I don't have to do any work because those will already cancel. So let's see, I have negative 14 and positive 3. That will give me negative 11x. I have negative 17 and plus 5y, which will give me negative 12y. My z's cancel just like what I wanted. And again, I didn't do substitution here because there was no isolated variable, but you could do that if you wanted to. Anyways, so I have negative 19 and 13, so it'll give me negative 6. Okay, so I'm going to call this equation number 4. We're going to do that again. I'm going to try to eliminate the z's, but using two different equations. So maybe I'll use equation 1 and 2, or I could use 2 and 3. It's up to you. I'm going to choose to use 2 and 3 because they already have opposite signs. So all I'd have to do is multiply this one by 2 instead of having to multiply by like a negative. So I'm going to combine 2 and 3. And I'm just going to rewrite these first just to keep it organized. So negative 5x minus 2y. Then I have minus 4z, and that equals 20. In my next equation, I have negative 14x minus 17y. I know a lot of scrolling here, sorry about that, plus 2z, and that equals negative 19. Okay, so if I want the z's to cancel, this needs to be a 4. So I'm going to make that a 4 by multiplying everything by 2. You can't just multiply a piece of it. You got to multiply the whole thing. If you just multiply a piece of it, you're changing the equation. So I'm just going to rewrite equation 2. I know this is getting tedious. Sometimes you don't have to rewrite it all, but I think it helps to just keep things organized. Okay, so I multiply all that by 2. I get negative 28x. I get negative 34y. I get plus 4z. And that equals negative 38. Okay, so let's add those together here. Okay, minus 28 and minus 5 will give me negative 33x. This will give me minus 36y. These will cancel like I wanted. And here I'll get negative 18. Okay, and that's equation number 5. Now something you should start looking for is the relationship between our equation 4 and our equation 5. And if you think about this one, equation 5 is just 3 times the size of equation 4. So if I multiply all these by 3, I will get equation 5. But let's look at that a little bit more by doing our next step. So if we're solving this system, we are going to add or combine or substitute, whatever you want to do, equation 4 with equation 5. So this is a negative 11x minus 12y equals negative 6, and negative 33x minus 36y equals negative 18. Now these aren't going to eliminate the way we have them right now, so I'm going to need to multiply something. And like I said, if I multiply this by 3, I'll get the same equation here. But in order for things to cancel, I have to multiply by the opposite sign because they all have the same sign. So that will give me positive 33x plus 36y equals 18. And I'm going to combine that with equation, that's supposed to be a 5. It doesn't really look like a 5, so let's change that. Okay, so I'm going to add that or combine that, do a linear combination with negative 33x minus 36y equals negative 18. Okay, notice as we go through this, so that's 0, that's 0, that's 0. So you get the true statement 0 equals 0. Which means no matter what you plug in for x and y and z, you're always going to get a true statement, which means that there's an infinite number of things that will give you a solution. So my final answer would be infinite solutions. So much to think about. Okay, so the step 4 would be to write your solution. Now, if I'm going to write my solution in 3 dimensions, if I had just one solution, I would write it as a 3-dimensional point. So a 2-dimensional point is x comma y. A 3-dimensional point is x comma y comma z, because you have 3 dimensions. Now, if I have infinite solutions, I can just write infinite solution. If I have no solutions, I can just write no solution. But there's a better way to write infinite solutions. And before I talk about that, I actually want to show you a visual. I found this, it's really cool. You can explore this on my website. But if you're curious what this actually looks like, what equations I'm actually solving, I plugged in my 3 equations here. And you can kind of rotate this around, and you can see that here's where the 3 planes intersect. So that's how you'd graph the 3 planes. And they all intersect at that green line. You can see it right here. That's where my infinite solutions are. Now to write my infinite solutions, I'm going to leave this for the next video, because this actually requires a little bit of conversation. So infinite solutions is how you're going to leave it for now. In the next time, you're going to learn a more precise way to write your solutions so we can actually define what the solutions are. Here's a system for you to try on your own, and have a great night.